Let us look at two more MOSFET biasing techniques. The first one is biasing using a drain-to-gate feedback resistor. It is implemented via this circuit. The large feedback resistance RG forces the DC voltage at the gate to be equal to that at the drain. That is why our current to the gate IG is 0. So we can write the equation, and making VDD the subject, we can write VDD equals VGS plus IDRD. This is identical to the equation where VG is fixed for biasing, except that here we have VDD and in that equation we had VG. However, the function is still the same. Again, if ID increases, VGS will have to decrease since VDD is constant. Decreasing VGS will in turn decrease ID, and hence it will be brought down to a stable value. So in this scheme, RG works as a negative feedback or degeneration resistance, and it works to keep the value of ID as constant as possible. However, as we will see later, this circuit has the drawback of a rather limited output voltage signal swing. It is, however, still more stable than the one in which VGS was fixed for biasing. Now let's look at our second technique. The second technique we are going to see is biasing using a constant current source. As you can see in the circuit, the current source is placed in the source terminal of the MOSFET. This is by far the best technique for biasing. To understand how it works, we first have to look deeper into the current source. Take a look at this expanded diagram. This is what the constant current source looks like, the diagram in the middle. To see how it works, let's start from our left, the transistor Q1. Notice that its drain is shorted to its gate, and therefore it is in saturation region. We can write the equation for its current as this equation. The drain current of Q1 is supplied by VDD through resistor R. So we can write another equation, ID1 equals IREF equals VDD plus VSS minus VGS over R. Do you agree? The IREF is the reference current of the current source. If we know IREF and the MOSFET parameters, we can easily find R. Now let's move on to the transistor Q2. Notice that it has the same VGS as Q1. We assume that it is operating in saturation, so we can write the equation for its drain current ID2 as this equation. Notice that both MOSFETs Q1 and Q2 have the same VT. They are identical except for one parameter, that is the aspect ratio W over L. For ID1 it is denoted by the subscript 1, and for ID2 it is denoted by subscript 2. The rest of the things are the same, so we can write a ratio, and so the reference current is hence now related to the desired current I. This circuit is known as a current mirror. The constant current source I is implemented using this current mirror. It is a very popular and very useful circuit in the design of IC, MOS amplifiers as well as discrete amplifiers. We are going to study that later. But now you have another quiz.